All right, so zeros of polynomial functions. The fundamental theorem of algebra tells us that if we have a polynomial of degree n, third degree, fourth degree, second degree, fifth degree, where n is greater than 0, some power greater than 0, then f has to have at least one 0 in the complex number system. Okay? Thus far, we had been working with zeros in the real number system. Now we're going to involve those complex numbers in those numbers or solutions, those zeros in the complex number system, so we can be including those imaginary numbers. Now it doesn't hurt to kind of talk about these so we keep remembering what these are. Natural numbers are our numbers that we learn when we're little guys. 1, 2, 3, 4, when we learn to count. We add 0 and now we have the whole numbers. You learn that there are 0 goldfish crackers left. You don't get any. Have to pick a different snack. Then we learn about integers. Mom says it's too cold to go outside. It's -3 degrees out. Sorry, you can't wear your snowsuit. It's too cold. So we throw our negative counting numbers in there. -17, -56, and so forth. Then we talk about rational numbers. Those rational numbers, fractions, decimals, things that terminate or repeat, 0.5, 2/3, -17 halves, etc. Then we add our irrational numbers in there. Those irrational numbers are things like the square root of 3, pi, e, and so forth. And finally, we say now that we can divide by a square root or have a square root of a negative number. Those are our complex numbers because that introduces the concept of I and having complex conjugates and things like that. Okay? So there's always going to be a 0. The linear factorization theorem says that if f of x is a polynomial of degree n, where n is greater than 0, so again, we've got some quadratic, some trinomial, a third degree polynomial, and so forth, then f of x has to have how many zeros? If n is the power, the highest power, how many zeros could it have? Yep, and factors. Now, they don't have to be unique zeros or unique factors, but it has to have that many zeros. Okay. Then, if f of x has zeros of 2 and -1 and 4i and -4i, could we write the linear factors of f of x? We did it before, right? The only thing that's changed is now we have some i's, some imaginary numbers. So if I said it has a 0 of 2, what's this factor going to be? X minus 2. If it has a 0 of -1, what's its factor going to be? Absolutely. If it has a 0 of 4i, its factor will be, and if it has a 0 of a -4i, then its factor will be exactly. Okay. So it hasn't changed, even though we're now in the complex number system, still behaves the same way. But let's think about this for a moment. If I were graphing, first of all, what power will this have? A fourth power, right? Fourth degree polynomial. If I were graphing this thing, I would have a 0 at 2 and a 0 at -1. And what about those i's? Going to be somewhere else, right? They're not going to cross the x-axis here, are they? So we're only going to have 2 real zeros. We're only graphing on the real coordinate plane. So those zeros are going to not appear on our coordinate plane. Does that make sense to everybody? Okay. So we have something called the rational zero test. If they asked us to solve x³ plus 6x minus 7 equals 0, That would be the first thing that would come to mind to try. Factor it, okay? This is a cubic. Can we factor a cubic? Not unless there's everybody has an x in common, right? Okay, so we'd have trouble with factoring. That's the first thing that we would think of. We'd think of completing the square. We'd think of quadratic formula. They only work with quadratics, highest power of 2. So the rational zero test says that if we have a polynomial of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1, notice the powers are descending, down to a sub 1 x plus a sub 0. So this is just a way of saying I've got some power, then a lower power with a coefficient, and another lower power with a coefficient, all the way down to a constant. And it has integer coefficients. Then every rational zero of it has to be of the form p over q. There's your most important piece here. The zeros have to be of the form p over q, where p is a factor of a sub 0, and q is a factor of a sub n. So in this example, we would want any factors of 7 divided by any factors of 1. So far, so good? Okay. So what are factors of 7? Good question. You're right, it's at negative 7, right? So factors of negative 7 are 7, negative 7, and 1, negative 1, right? And factors of 1, 1, and it could also be negative 1 times negative 1, right? So when you're writing these out, you can write them as plus or minus 1 and plus or minus 7 over plus or minus 1. So we have a total of 6 different, or let's see, 2, we have 1, 7, negative 1, negative 7, total of 4 different possibilities for this one. And if none of those worked, there are no rational zeros for this particular equation. Okay? So we can eliminate some of the guessing. So let's pick an example here. X cubed minus 7x plus 6, or minus 6. How many zeros will I have? At least one, but most likely 3 with some kind of multiplicity, right? Potentially. Okay? Then we say factors of what over what are our possible zeros? Factors of negative 6 over factors of 1. So what are some factors of negative 6? Plus or minus 2, plus or minus 3, plus or minus 1, and plus or minus 6 over plus or minus 1. So there are 8 possible zeros there. So what process will we use to figure out which one it is? Synthetic division. So we have a 1x cubed. We don't have any x squareds. We have a negative 7. We have a negative 6. Which of those 4 do you want to try first? 1. Okay, we're going to try 1 first. And what are we hoping to achieve over here? 0. Okay. So we're dropping a 1. 1 times 1. Add. 1 times 1. Add. Negative 6. 1 times negative 6. Close, but no cigar. -1 was suggested. So you can rewrite it, keep rewriting it, but you can also do this. If it doesn't mess you up. Okay? You can say, okay, I'm going to drop my 1. 1 times a -1 is -1, -1 and 0. -1 times -1, 1, 1 and -7. -1 times -6, 6, 6 and -6. It worked. Okay, so we can eliminate this middle row if you want to. It'll scrunch things together. Make sense? Okay. Now what kind of equation do we have? A squared. It's been depressed. So now we have an x squared minus x. I want to write a -6. See if my eraser will work today. Of course not. Oh, there it did. X squared minus 6. Wrote it again. Try that one more time, but at least I know that the eraser works if I do the full eraser, not just a tip. X squared minus x minus 6. All right. Now can we factor that? I think so. X and x. And a negative and a positive. Which one needs to be negative? 3, 2. So we want to find the zeros. We don't want to stop with factors. So x equals -2, 3, and -1, which were all in our predictions, weren't they? Okay. Now, sometimes you'll get lucky and you'll guess the first one right away, and it will take very little time. Sometimes you won't. You need to be patient with these and take your time on these. I didn't give you very many problems because of that. Question? Okay. So you don't have to test all of them. Absolutely not. Just find one, and then if it's a trinomial now, or trinomial that, or a third power, then it's going to be a quadratic, and you can try to factor it or use quadratic formula or complete the square. Okay? But if it was a fourth one to begin with, you'll have to get it down one more time, find another one. Okay? These are just all the possibilities. These are the actual real roots. If it's squared to begin with, you can use quadratic formula or, yep. Okay? Do you want to see another one, or are you guys okay? Everybody okay? Don't need to see another one of those worked? Okay. All right, conjugate pairs. Conjugate pairs are of the form a plus bi and a minus bi. They always travel in pairs. So you can't have an a plus bi as a root without an a minus bi as a root. Kind of like when we had a square root of 3, we also have to have a negative square root of 3 as our answer. So if a plus bi is a 0, a minus bi, the conjugate of it, is going to be a 0 as well. So find a 4th degree polynomial. You guys need more time? I'm sorry. You don't have to copy everything down. I wouldn't copy all the verbiage, you know, this is a formal presentation of it. So when I'm taking notes, I just say a plus bi and a minus bi travel in pairs. Okay? A plus bi and a minus bi have to follow together in pairs. They have to be in this, they go together. Like matching socks. Okay, so find a 4th degree polynomial with these zeros. 0, 1, and I. 4th degree polynomial should have how many zeros? 4. It's only listed 3 of them. Do we know what the 4th one would be? is negative I, because they always travel in pairs. Okay? Well, x minus 0 would be our first factor, right? In order to get a polynomial, we've got to have some factors to multiply out. So this is just good old x. This one's going to be what? X minus 1. This one's going to be x minus I. Good. And the other one's going to be x plus I. So in section 2.4, you learned how to multiply those guys, or remembered how to multiply those guys. We're going to go ahead and multiply the conjugates out first, right? That way we're going to make it look like something that is real. So x times x, outsides, insides, last. So this is going to be an x squared, negative x squared, or negative I squared is plus 1. Yep. Okay. So that's one factor. Don't forget these two as well. If you want to call it x squared minus x, that's okay. And then we're going to multiply them out. So x squared times x squared. Outsides. Insides, it's a negative x and a positive x squared. And a negative x times a positive 1. So write it in descending powers. There's our 4th degree polynomial with those as zeros. So we can say, here's the zeros, give me the polynomial. And we can say, here's the polynomial, tell me what the zeros are. Fourth degree polynomial, how many zeros will it have? 4. There could be some multiplicity going on there though, right? They may not all be unique. And 2 plus 3i is a 0. So what do we do? Got another one, 2 minus 3i is going to be another 0, because they always travel in pairs. So we have a couple of options. We could try synthetic division with the i's, or we could say one of my factors is x minus 2 minus 3i, and my other factor is x minus 2 plus 3i. And multiply those two together, I'll have an x squared something, and I can do long division. Okay. So x times x, then x times the middle, x times the last. Now I've got to take my negative 2 times everybody. Negative 2 times x, negative 2 times a negative 2, positive 4, negative 2 times a positive 3i. Now I have to take my 3i times everybody. Negative 3i times x, negative 3i times a negative 2, negative 3i times a positive 3i is going to be a negative 9i squared plus 9. X squared, negative 4x, gone. Those guys will be gone. 4 and 9 is a total of. So we have an x to the 4th. Give myself much space here. x to the fourth minus 4x cubed plus 12x squared plus 4x minus 13 being divided by x squared minus 4x plus 13. And it should divide out correctly with no remainder, right? Or we've made a mistake somewhere. So x to the fourth times what gives me, x squared times what gives me x to the fourth? So x squared times x squared, negative 4x times x squared, negative 4x, or 13 times x squared. Change your signs. So we add those up, x to the fourths are gone, 4x cubes are gone, and I'm getting simply a negative x squared. Bring my 4x down, and my minus 13, sorry. What do I have to take x squared times to get a negative x squared? Negative 1, right? So negative x squared, negative 4x times a negative 1, positive 13 times a negative 1. Change my signs. Almost there. So we know 2 plus 3i is a 0, 2 minus 3i is a 0, and x squared minus 1 is a factor. What do we do with this x squared minus 1? X minus 1, x plus 1. So 2 plus 3i, 2 minus 3i, and positive and negative 1. Big problems. Not very many coming to you. Okay. All right, assignment. This is a 2-day kind of thing. We're spending 2 days on 2.5 because there's a lot going on. Yes, sir. Yep. So the fraction itself comes from the fact that they'll always be of the form negative p over, or plus or minus factors of p over q. So factors of your constant over your factors of your leading coefficient. Okay, IO. Yep. Yep, they gave us 1, 0. They have to travel in pairs. The complex conjugates, if a plus bi is one of them, then a minus bi will also be another one. Okay, so that's they're giving you a give me. So a is your we defined it yesterday. We have a real part plus an imaginary part, and so they just call it the real part a and the imaginary part b times I. So if it's 2 plus 3i, your a is 2 and your b is 3. And so these guys are always going to travel in pairs. So if 2 plus 3i is one of your zeros, 2 minus will be another. This is 2.5. So this will be due, if we want to put them together and work on it for 2 days and turn in them both at the same time, that's fine. But we're going to do page 164, 19, 22, 30, 45, 47, 55, and 59. Only 7 problems. But if you find that you're not getting zeros right away, take your time, look through your signs. They're not all long. No. Some of them are just going to say, here are zeros, tell me factors. It's when you have to take the polynomial and bring it back to the zeros that it takes a bit of time.